amorphous solids. Solid state of matter, as you have studied in your high school lessons, is characterized by a dense and ordered arrangement of constituent particles, which can only vibrate about their mean positions. Is it then possible that for all solids, there is one basic unit which, when repeated in the x, y and z directions, will generate the entire 3D structure of the solid? Well, solids like copper metal, in which this happens, are called crystalline solids. As you can see, the arrangement of copper atoms is the same in all directions through this copper block. Crystalline solids are thus said to exhibit long-range order. Diamond, sodium chloride, and copper metal are a few examples of crystalline solids. However, all solids do not exhibit this kind of an arrangement. For example, in glass, a periodically repeating arrangement is observed over short distances only. Such portions are scattered, and in between the arrangement is disordered. Solids like glass are therefore said to exhibit a short-range order and are called amorphous solids. Let us study a few properties of each of these categories of solids. Crystalline solids. Sodium chloride is a very common example of a crystalline solid. Observe a sample of sodium chloride at a molecular level. The constituent particles, namely sodium ions and chloride ions, are bonded together in a regular pattern such that each sodium ion is surrounded by 6 chloride ions, and each chloride ion is in turn surrounded by 6 sodium ions. The smallest unit of a crystalline solid is known as its unit cell. This unit cell is repeated again and again in all the directions to form the entire structure of the crystal. Let us now heat this sodium chloride. The constituent particles absorb this heat energy and start vibrating faster. Being equal in strength, the bonds between the constituent sodium and chloride ions break at the same time, and the entire solid melts at one go. In other words, crystalline solids have extremely sharp melting points. This can be verified graphically as well. Notice that the temperature remains constant at 801 degrees Celsius till all the sodium chloride melts. Crystalline solids are anisotropic in nature. If in a material, optical, mechanical and electrical properties are different along different directions, it is said to be anisotropic in nature. For better understanding, let us study the optical property of calcite crystal. In a calcite crystal, refractive index has different values, that is, 1.4 and 1.6 along different directions. It can be experimentally shown that even mechanical and electrical properties in the crystal have different values along different directions. Let us now compare these properties of crystalline solids with those of amorphous solids. Amorphous solids. As discussed earlier, unlike crystalline solids that are characterized by the regular arrangement of the constituent particles, amorphous solids show no regularity in the arrangement, as in the case of glass shown here. What happens if an amorphous solid is heated? Well, as you can see, due to the random arrangement of particles, different bonds have different strengths. Those having lower strength break at once, but the stronger ones require more heat to break. Thus, melting continues as the temperature keeps rising until the entire melting takes place. In other words, Amorphous solids do not have sharp melting points, but melt over a range of temperatures. Amorphous solids are isotropic in nature. If in a material, optical, mechanical, and electrical properties are the same along different directions, it is said to be isotropic in nature. Unlike crystalline solids, which are anisotropic, amorphous solids are isotropic in nature. For example, in a glass slab, the value of refractive index is the same, that is about 1.5 along any direction. Summary: solids are mainly classified into two types: crystalline solids and amorphous solids. Unlike crystalline solids that are characterized by the long-range order of the constituent particles, amorphous solids exhibit short-range order. In contrast to crystalline solids, which have a sharp melting point, amorphous solids do not have a sharp melting point. Crystalline solids are anisotropic, but amorphous solids are isotropic in nature.